So good day. So next I am going to discuss about another modern engineering material which is called superalloys. So from the name itself it is clear that it is an alloy. Before discussing about superalloys, let me explain the need of superalloy. So see this is a jet engine cross section, and here in this jet engine we have different parts. There is a fan in the front area, then low pressure compressor, then this is the high pressure compressor, and this is the combustion chamber, and we have a high pressure turbine, then low pressure turbine. So these are the different main parts of a jet engine. And see this what is the temperature during its operation, what is the temperature developed inside this jet engine. So here in this this fan area subjected to ambient air, so it will be atmosphere temperature. But when the air enter here it has a temperature of 200 degrees Celsius. Then in this high pressure combustion or area, it's increased to 600 degrees Celsius. Then in the combustion chamber, it is around 1100 degrees Celsius. Then in the low pressure turbine area, it is 700 degrees Celsius. So that is the distribution temperature inside the jet engine during its operation stage. So here we are using different types of material. So here in the inlet area where the temperature is very low, we can use composites, and here in this low density aluminum materials are used. Here we use titanium. Here in this two area where again it is a low temperature region where we use steel. But here this area is very important. This area where we use superalloys. So superalloys is the main need of superalloys is the development of parts or components where where the temperature is very high. Where the temperature is very high. So in this area we are using superalloys. Okay. So that is the important need of superalloys. So that is the amazing property of the superalloys. They become stronger at a higher temperature. Okay, so we can use or we can select a material that is superalloy material which is very strong and high temperature. So that is the important property of a superalloy. See the specific strength of different material with respect to temperature. So when the temperature increase, what happened to different material? See this aluminium. With respect to increase in temperature, the material specific strength of the material is decreasing. For steel, this is also decreasing. For the titanium alloy, up to a moderate temperature, it has very good strength. But after at a high temperature, it's again decreasing. But see this red colored superalloy, say nickel alloy. Nickel alloy is that is a one type of superalloy. See this, it maintain a constant strength up to very high temperature. Okay, up to even and very close to the melting point of nickel. This material, superalloy material, show very high strength at a high temperature. So that is the important property of a superalloy. So we can define a superalloy. Superalloys are high temperature alloys used in jet engine, gas turbine, and reciprocating engine. Okay, and what are the important characteristics of a superalloy? It is able to maintain high strength at a high temperature. So that is the important property of a superalloy, able to maintain high strength at a high temperature. So actually the development of superalloy is for this application. Especially during the Second World War 1930. So every country participated in this Second World War, trying to develop engines with a very high velocity, the aircraft with a very high velocity. So they need very high efficiency engines, jet engines. For that, for higher efficiency, we know based on the Carnot cycle, if the heat supplied minus heat rejected by heat supplied is the efficiency. So if we can increase the heat supplied, then efficiency also will increase. So how can we increase the heat supplied? By supplying gas or air with a higher temperature. So if the temperature is increased, what happened to the material? If we use the ordinary steel or ordinary material, what happened? Its strength will decrease. So there is a chance for the damage of the engine. So we need a material that has very high strength at a high temperature. Thereby we can develop an engine with a higher efficiency. So that is actually the driving force for the development of the superalloys. So it has a very high strength at a high temperature. And next important properties is corrosion resistance. It has a good corrosion resistance and oxidation resistance at a high temperature. That is also important. And next one is the good resistance to creep and rupture at a high temperature. The most of the material which show creep deformation at a high temperature. So that is the main failure criteria for the material at a high temperature. So this superalloy material show a good resistance against creep at a very high temperature. So these three are the main three important property of a superalloy. So there are three classes of superalloys: nickel-based superalloys and cobalt-based superalloys and iron-based superalloys. So nickel, cobalt and irons are the base metal, and we use different alloy elements in this for the development of superalloy. So what is the main important property of nickel? The important property of nickel is this one: it maintains FCC crystal structure throughout the melting temperature. Up to melting temperature, it has a FCC crystal structure. But in case of iron, this is not true, because there will be allotropic or polytropic change in the iron. First it will be ferrite, then austenite, then delta ferrite. So it has BCC structure, FCC structure, again BCC structure. So there will be a polymorphism or polymorphic transformation for iron, but such a polymorphic transformation is not showing in case of nickel. Nickel throughout its temperature it shows FCC crystal structure. So this FCC crystal structure is very good for higher strength at a high temperature. I will explain about that later. And next one, cobalt. We use cobalt developed cobalt based superalloys, and it has a HCP crystal structure at room temperature, but at higher temperature it has a FCC crystal structure. And iron based superalloys, we know between 910 degrees Celsius and 1400 degrees Celsius, iron is in austenite state. Austenite is in FCC crystal structure. So here we can see a one common thing in these three cases for nickel, cobalt and iron. We can see a common thing, that is at a high temperature every material, the iron, nickel and cobalt, showing FCC crystal structure. So next I will explain the importance of FCC crystal structure. FCC crystal structure or face-centered cubic crystal structure. Where do we want FCC crystal structure? So we know FCC crystal structure are more close packed. If you consider the atomic packing factor of FCC crystal structure, it is more close packed than that of the BCC crystal structure. So because of the very close packed structure, what is the advantage? Hence diffusibility are very low, so the creep resistance will be very high at a high temperature. So the chance for diffusion will be very less in FCC crystal structure. That is why these three material is selected for the development of superalloys: nickel, cobalt and iron. And we use some stabilizers to stabilize the close path structure for high temperature applications. We can maintain this FCC crystal structure even for this iron. For example, in case of iron, in between 910 and 1400 only we have FCC crystal structure. But using different stabilizers, we can reduce this 910 degrees Celsius and we can increase the 1400 degrees Celsius. Thereby the gap between, or the austenite state, the temperature required for the austenite crystal structure can be increased by using different stabilizers. But next question is, why we are not using tungsten for making the superalloys? Tungsten, we know the tungsten melting point is around above 3000 degrees Celsius. So its melting temperature is very higher than that of all this material, titanium, nickel, steel, aluminum. But we are not using tungstens to make these superalloys? What is the reason for we are not using tungsten to make these superalloys? The answer is this one: tungsten has BCC crystal structure at a high temperature, so the creep resistance will be very low for tungsten. That is why we are not using tungsten for making. Even the melting point is very high for tungsten, but strength at close to the melting point is very low for tungsten. So that is why we are not using tungsten for making superalloys. So based on this, using this based nickel based superalloys, mainly there are, this is the two superalloys commonly used, mnemonic 75 and mnemonic 80. 75% nickel and 19.5% chromium, and for 80 it is 80% nickel and 19.5% chromium. And also we add titanium and aluminum, and this titanium and aluminum produce intermetallic compounds which is precipitate and give additional strength for superalloys. So how this superalloy strength is increased at a very high temperature? So that is explained with these three terms. The first reason for the higher temperature is solid solution hardening, and second strengthening mechanism is the precipitation of the intermetallic compounds, and third reason for the strength, higher strength at a higher temperature is the formation of carbates. So these are the three reasons for the very high strength of nickel based superalloys at a higher temperature. So before that, I will explain these three terms: solid solution strengthening, precipitation strengthening, and carbide phases strengthening. So we already know what is solid solution strengthening. That is nothing but it is alloying. So we know what is alloying. There will be a regular crystal lattice of the base metal. Okay, this is the base metal crystal lattice. And when we add any impurity atom, so this is another impurity atom. This impurity atom, either it occupies the interstitial position, or it occupies in by substitution. Okay, that is substitution solid solution or interstitial solid solution. So by this formation of solid solution, what happened? It hinder or resist the dislocation motion, thereby strength is increased. So that is called solid solution strengthening. So in nickel based superalloys, nickel is the base metal, and what are the different alloy elements? Chromium, molybdenum, aluminum, niobium, titanium, etc. are the alloy elements. So when we add these alloy elements, what happens? These alloy elements occupy either interstitially or substitutionally, and which hinder the dislocation motion, thereby strength is increased. So that is the first reason for the higher strength at a higher temperature of the nickel based superalloys. Second reason is the precipitation hardening. So when we add aluminum and titanium, this aluminum and titanium form an intermetallic compound with the nickel. Okay, so Na3Al or Na3Ta are the secondary precipitates formed in the primary phase, and these secondary precipitates actually hinder the dislocation motion, and thereby we can improve the strength. So that is also, so for example, this is grain, this is the primary nickel grain boundary. Okay, primary nickel grain boundary. In this primary nickel grain boundary, Na3Al or Na3Ta intermetallic compounds are formed, and these intermetallic compounds actually precipitate in a finer precipitate. We can see the finer precipitate in these grains, and these finer precipitates, this is the finer precipitates. Okay, and this finer precipitates is called gamma prime. So this gamma prime retard the or resist the dislocation motion, and thereby we can improve the strength. So that is the precipitation strengthening. So intermetallic compounds Na3Al or Na3Ta precipitate in the primary phase of nickel, and this precipitate improve the strength of the alloy, superalloy. And third one is the carbide formation. The M23C6 or M6C or MC type of carbides are formed along the grain boundary, which also increases the strength of the nickel-based superalloys. Okay. So here I am only explaining the nickel-based superalloy because this nickel-based superalloys is commonly used in the modern engineering application. So this is what I explained, the three reasons for the strength of the nickel-based superalloys. First one is the solid solution strengthening. A gamma phase is formed. That means either substitutional solid solution or interstitial solid solution. And in this, we have chromium, molybdenum, aluminum, niobium, titanium, etc. alloy elements. These alloy elements substitutionally or interstitially occupy in the base metal, and thereby an alloy is formed or a solid solution is formed, and this solid solution strengthens the material, superalloy material. So that is the first one. Second one is the gamma prime phase or precipitation strengthening. I already explained this precipitation strengthening is because of these intermetallic compounds are precipitated along the primary phase. Finer precipitates are formed. This also resists the dislocation motion, thereby the strength of the material can be improved. And another one is the gamma double prime phase, and that is also strength the material at a lower temperature, and some carbides and the borates also improve the strength of the nickel based superalloys. That is also already I am explained. So these are the three strengthening mechanisms. So first one is the by the addition of different alloy elements. What are the alloy elements? These are the alloy elements. Okay, alloy elements we can improve the strength. Second one is the gamma prime precipitates, intermetallic compounds produce, and carbides and borates. Carbon are often present at a concentration of up to 0.28%, combined with reactive elements like titanium and tantalum, hafnium, and form MC. Okay. So where M is nothing but it will be either aluminum or titanium or tantalum, etc. So these carbides are formed, and during the service life it may decompose into M23C6, where M is nothing but it is the any of this metal element. Okay, and these carbides and borates precipitate or segregate along the grain boundary, and which improve the strength. So that is actually explained here. The first is solid solution strengthening. That second one is the prime alpha prime strengthening. So here this intermetallic compound with the general A3B structure. A nothing but nickel, 3B may be aluminum or titanium. Okay, it has again FCC crystal structure, and which is a closed pack structure. And here in this A3B structure, A will be in the face center of the FCC structure, and B will be in the body contact points. And another strengthening mechanism is dispersion strengthening. Yttrium oxide and thorium oxide, aluminum Al2O3, etc. may displaced in the there will be displaced phase in the material, and that also increases strength. And the formation of carbides or borates at the grain boundary also increase the strength of the material. So this is the carbides. We add carbides or carbon content 0.05 to 0.2%, and these carbides combined with some refractory elements form TAC or HFC. And during the heating of these carbides begins to decompose and form lower carbides, such as during its service life it form M23C6 or M6C, which tends to generate on the grain boundary. Okay, where M is the nothing but it is chromium or iron or tungsten or molybdenum. Okay, and these carbides and borates segregate along the grain boundary, which increase the strength of the material. Okay, so what are the applications? There are different applications. We know different area where high temperature is involved. So under any area where high temperature is involved, we can use superalloys. For example, aerospace gas turbine engine, where in the combustion chamber we can use superalloys. In space vehicle rocket engine, where in the high temperature area we can use superalloys. Nuclear reactor, power generation turbine, submarines, and petrochemical equipment, high temperature fasteners, combustion engines, exhaust valve, hot working tool and dies. Everywhere wherever the high temperature is involved, we can use this superalloy. Okay, that is the application of superalloy, and this is about superalloys. The main important characteristics of a superalloy is that it is very useful in the high temperature area. It can maintain very high temperature and high strength and even high toughness also at a high temperature, and it is very good corrosion resistance and creep resistance. Okay, and study these strengthening mechanisms of the superalloys also. Okay, thank you.